Dear friends, today we are discuss about engineering materials. My name is Dr. N. Sri Rangarajulu. I am assistant professor in the Department of Production Technology, MIT campus, Anna University, Chennai. Day-to-day applications, we are able to use so many number of materials. Especially today we are discuss about the ferrous and non-ferrous materials and their properties and their application, so on. So engineering materials and their properties. Introduction. Material science and engineering plays a vital role in this modern age of science and technology. Various kinds of materials are used in industry, housing, agriculture, transportation, etc. to meet the plant and individual requirements. The knowledge of materials and their properties is a great importance for a design engineer. A design engineer must be familiar with the effects which the manufacturing processes and heat treatment have on the properties of the materials. The engineering materials are mainly classified as metals and their alloys such as iron, steel, copper, aluminum, etc. Non-metals such as glass, rubber, plastics, etc. Metals may further be classified as ferrous materials and non-ferrous materials. Ferrous materials are those which have the iron as their main constituent, such as cast iron, wrought iron, etc. Non-ferrous metals, the non-ferrous metals are those which have metals other than iron as their main constituent, such as copper, aluminum, brass, tin, zinc, etc. The physical properties of engineering materials. The physical properties are employed to describe the response of material to imposed stimuli under the condition in which external forces are not concerned. Physical properties include dimensions, appearance, color, density, melting point, porosity, structure, etc. Dimension of a material implies its size, length, breadth, width, diameter, etc. and a shape, square, circular, channel, angle, section, etc. Appearance. Metals themselves have got different appearances. Example, aluminum is a silvery white metal, whereas copper appears brownish red. Appearance include luster, colors, and a finish of material. Luster is the ability of material to reflect light when finely polished. It is the brightness of the surface. Color. The color of the material is very helpful in identification of metal. The color of the metal depends upon the wavelength of the light that the metal can absorb. Density. The density is the weight of unit volume of material expressed in metric units. Density depends to some extent on the purity of the material, pore volume, treatment the material has received. Density helps differentiating between light and heavy metals, even if they have some shape and any outer protective coatings. Melting point. Melting point of the material is the temperature at which the solid metals change into molten state. One metal can be distinguished from the other on the basis of its melting point. Porosity. A metal is said to be porous if it has pores within it. Pores can absorb lubricant as in the sintered self-lubricating bearings. It is the ratio of total pore volume to bulk volume. Structure. It means geometric relationship of material components. It also implies the arrangement of internal components of matter, electron structure, crystal structure, and microstructure. Chemical properties. A study of chemical properties of material is necessary because most of the engineering materials when they come in contact with other substances with which they can react tend to suffer from chemical deterioration. The chemical properties describe the combining tendencies, corrosion characteristics, reactivity, solubilities, etc. of substance. Some of the chemical properties are corrosion resistant, chemical composition, acidity, and alkalinity or alkalinity. Corrosion. It is the deterioration of a material by chemical reaction with its environment. Corrosion degrades material properties and reduces economic value of the material. Corrosion attacks metals as well as non-metals. Corrosion of concrete, of sulfate in soils is a common problem. Performance requirements. The material of which part is composed must be capable of embodying or performing a part's function without failure. For example, a component part to be used in a furnace must be of that material which can withstand high temperatures. While it is not always possible to assign quantitative values to these functional requirements, they must be related as precisely as possible to specified values of most closely applicable mechanical, physical, electrical, or thermal properties. Materials reliability. Reliability is the degree of probability that the product and the material of which it is made will remain stable enough to function in service for the intended life of the product without failure. The material, if it is corrodes under certain conditions, then it is neither stable nor reliable for those conditions. Safety. A material must safely perform its function, otherwise the failure of the product made out of it may be catastrophic in airplanes and high pressure systems. As another example, material that gives off spark when stuck or safety hazards in a coal mines. Next, we will discuss about engineering materials and their properties, especially for ferrous materials and their alloys. Ferrous materials and their alloys, plastics and other things we will discuss in the further videos and other things. Characteristics of ferrous materials. The ferrous materials are metals or metal alloys that contain iron as a base material. Steel is a ferrous alloy, and there are a number of other alloys that contain iron. Ferrous metals are good conductors of heat and electricity. Metal alloys have high resistance to shear, torque, and deformation. The thermal conductivity of metal is useful for containers to heat materials over a flame. The principal disadvantages of many ferrous alloys are their susceptibility to corrosion. Application. Due to the strength and resilience of metals, they are frequently used in high-rise buildings and bridge constructions, most vehicles, many appliances, tools, pipes, non-illuminated signs, and railroads, tracks, etc. Corrosion resistance properly makes them useful in food processing plants. Example, steel. Cast iron is strong but brittle, and its compressive strength is very high. So used in castings, manhole covers, engine body, machine base, etc. Mild steel is soft, ductile, and has high tensile strength. It is used in general metal products like structural, workshop, household furniture, etc. Carbon steels are used for cutting tools due to their hardness, strength, and corrosion resistance properties. So classification based on engineering alloys. Classification of alloys: ferrous alloys, non-ferrous alloys. Ferrous alloys itself, steels, cast iron. Steel itself, you will have a low alloy steel, high alloy steel. Low alloy steels, low carbon steel, medium carbon steel, high carbon steel. High alloy steel further classified as tool steel and stainless steel, etc. So now steel is an alloy of iron and carbon in which carbon content is up to 2%. It may contain other alloying elements. Cast iron, in cast iron, carbon content is 2 to 6.67%, lowering melting point about 300 degrees centigrade, lower than the pure iron, due to the presence of eutectic point at 1153 degrees centigrade and more carbon content. Type of cast iron: gray cast iron, white cast iron, nodular cast iron, malleable cast iron, and compacted graphite cast iron, so on. Low carbon steel, carbon content in the range of 0 to 0.3%. The most abundant grade of steel is low carbon steel, greatest quantity produced and least expensive, non-responsive to heat treatment, cold working needed to improve the strength. It has a good weldability and machinability. Medium carbon steel, carbon content in the range of 0.3 to 0.8%. It can be heat treated, austenitizing, quenching, and then tempering. Most often used in tempered condition, tempered martensite. Medium carbon steels have low hardenability. Addition of chromium, nickel, molybdenum improves the heat treating capacity. Heat treated alloys are stronger but have lower ductility. Typical applications: railway, wheels and tracks, gears, crankshafts, etc. Medium carbon steels are used for typical applications in railway wheels and tracks, gears, crane, crankshafts, etc. And high carbon steel carbon content is 0.8 to 2%. High carbon content provides high hardness and strength, hardest and least ductile. Used in hardened and tempered condition, strong carbide formers like chromium, vanadium, tungsten are added as alloying elements to form carbides of these materials. Used as a tool and die steels owing to high hardness and wear resistant property. Tool steel refers to a variety of carbon and alloy steels that are particularly well suited to be made into tools. Their suitability comes from their distinctive hardness, resistance to absorption, their ability to hold a cutting edge, and or their resistance to deformation at elevated temperatures. Tool steels is generally used in heat-treated state. Many high-carbon tool steels are also more resistant to corrosion due to their higher ratios of elements such as vanadium. With a carbon content between 0.7% and 1.5%, tool steel are manufactured under carefully controlled condition to produce the required quality. Stainless steel does not readily corrode, rust, or stain with water as ordinary steel does, but despite the name, it is not fully stain proof, most notably under low oxygen, high salinity, or poor circulation environments. There are different grades of surfaces, finishes of stainless steels to suit the environment. The alloys must endure. Stainless steel is used where both the properties of steel and the corrosion resistance are required. Stainless steel differs from carbon steels, may be amount of chromium present. Plain carbon steel. Plain carbon steel is an alloy of iron and carbon with carbon content up to 1.4%, although other elements such as silicon, manganese may be present. The properties of carbon steel are mainly due to its carbon content. Carbon steel is classified into low carbon steel or mild steel, medium carbon steel, high carbon steel, etc. So low carbon steel or mild steel. Low carbon steel or mild steel is further classified into 3 types based on their composition, that is the presence of carbon content. Dead mild steel or mild steel containing 0.05% to 0.15% of carbon. Mild steel containing 0.15% to 0.2% of carbon content. Another mild steel containing 0.2 to 0.3% of carbon content. Dead mild steel is application of mild steel. Dead mild steel is used for making steel wires, sheets, rivets, screws, pipes, nails, chains, etc. Mild steel containing 0.15% to 0.2% of carbon is used for making camshafts, sheets, strips for blades, welded tubes, forgings, drag lines, etc. Mild steel containing 0.2% to 0.3% of carbon is used for making valves, gears, crankshafts, connecting rods, railway axials, fish plates, and small forgings, etc. Medium carbon steel, steel containing 0.3% to 0.7% of carbon is known as medium carbon steel. Medium carbon steel are of three categories. Steel containing 0.3% to 0.45% of carbon is used for connecting rod, wires, and rod, spring clips, gear shafts, key stock, shafts, and brakes, levers, axials, small and medium forgings, etc. Steel containing 0.45% to 0.55% of carbon is used for railway coaches axials and crank pins, and heavy machines, spline shafts, crankshafts, etc. Steel containing 0.6% to 0.7% of carbon used for draw forging dies and die blocks, clutch discs, plate punches, set screws, valve springs, cushion rings, thrust washers, etc. High carbon steel, steel containing 0.7 to 0.15% of carbon is known as high carbon steel. Uses of high carbon steel, steel containing 0.7 to 0.8% of carbon is used for making cold chisels, wrenches, jaws for vice, pneumatic drill bits, wheels for railway service, wire for structural work, shear blades, automatic clutch disc, axes, etc. Steel containing 0.8 to 0.9% of carbon is used for making rock drills, railway drill, circular saws, machine chisels, punches and dies, clutch discs, leaf springs, music wires, etc. Steel containing 0.9% to 1% of carbon is used for making punches and dies, leaf and coil springs, keys, speed discs, pins, shear blades, etc. So uses of high carbon steel continues. Steel containing 1.0 to 1.1% of carbon is used for making railway springs, machine tools, mandrels, taps, etc. Steel containing 1.1 to 1.2% of carbon is used for making taps, thread metal dies, test drills, knives, etc. Steel containing 1.2% to 1.3% of carbon is used for making files, metal cutting tools, reamers, etc. Steel containing 1.3 to 1.5% of carbon used for making wire drawing dies, metal cutting saws, paper knives, tools for turning chilled iron, etc. Next, alloy steels. Steel is contained to be alloy steel when the maximum of range given for the content of alloying elements exceed one or more of the following limits: manganese, silicon, copper, or in which a definite maximum quantity of any of the following elements is specified: aluminum, bismuth, chromium, up to 3.99%, copper, molybdenum, nickel, titanium, tungsten, vanadium, or any other alloying element added to obtain a desired alloying effect. So, low and medium alloy steel. A low and medium alloy steel alloying elements is not exceeded 10%. First symbol 100 times of average percentage of carbon. Second, fourth, sixth, etc. symbol elements. Third, fifth, seventh, etc. symbol percentage of elements multiplied by factors as follows: elements chromium, cobalt, nickel, manganese, silicon, and tungsten. Multiplying factor is 4. Aluminum, barium, vanadium, bismuth, lead, copper, niobium, titanium, tantalum, zirconium, and molybdenum. Multiplying factor is 10. Phosphorus, sulfur, nickel. niobium, I think 100% multiplying factor. Least element, it indicates special characteristics. High alloy steels, in high alloy steels, total alloying elements are more than 10%. For example, X10 chromium 18 nickel 9 sulfur 3. X high alloy steel 10%, 0.1% of carbon, chromium 18 to 18% of chromium, nickel 9 to 9% of nickel, sulfur 3%, 3, that is a pickled condition. Tool steel may be defined as special steel which are used to form, cut or otherwise change the shape of the material into the finished or semi-finished product. Properties of tool steel: slight change of form during hardening, little risk of cracking during hardening, good toughness, good wear resistance, very good machinability, a definite cooling rate during hardening, a definite hardening temperature, resistant to decarbonization, resistant to softening on heating. These are all the properties of tool steel. Classification of tool steel: the Joint Industry Conference USA has classified tool steel as follows. Symbol T, that is the meaning of meaning is W, high speed steel, tungsten high speed steel. M, molybdenum high speed steel. D, high carbon high chrome steel. A, air hardened steel. O, oil hardened steel. W, water hardened steel. H, hot work steel. S, shock resistant steel. Like that, they are able to classify. Composition of tool steel: W, tungsten high speed steel, T1, T4, T6, molybdenum high speed steel, M1, M6, high carbon high chrome steel, D2, D5, D7, and air hardened steel, A2, A7, A9, and oil hardening steel, O1, O2. Water hardened steel, W2, W5, hot work steel, H10, H12, shock resistant steel, S1, S2, S5, S7, so on. So stainless steel, when 11.5% or more chromium is added to iron, a fine film of chromium oxide forms spontaneously on the surfaces. The film acts as a barrier to retard further oxidation, rust, or corrosion. As the steel cannot be stained easily, it is called stainless steel. The stainless steel, basing on their microstructure, can be grouped into three metallurgical classes such as austenitic stainless steel, ferritic stainless steel, and martensitic stainless steel. So austenitic stainless steel properties: they possess austenitic structure at room temperature. They possess the highest corrosion resistance of all stainless steels. They possess greatest strength and scale resistance at high temperatures. They retain ductility at temperature approaching absolute zero. They are non-magnetic. Composition will be this is carbon content is 0.03 to 0.2%. Other elements are percentages given below. And next, the uses of austenitic stainless steel: aircraft industry, engine parts; chemical processing industry for heat exchangers; food processing industries for kettles, tanks; household items for cooking utensils; dairy industries for milk cans; transportation industry for trailers and railway cars, etc. And the ferritic stainless steels properties: they possess a microstructure which is primarily ferritic. They magnetic and have good ductility. They do not work harden to any appreciable degree. They are more corrosion resistant than martensitic steel. They develop their maximum softness, ductility, corrosion resistance in the annealed condition. Composition: 0.08% to 0.2% of carbon. Remaining other things: silicon, manganese, and chromium, etc. Chromium 11 to 27% of chromium. That is a ferritic stainless steel. Uses of ferritic stainless steel: lining for petroleum industry, heating elements for furnaces, interior decorative works, screws and fittings, oil burner parts, etc. Martensitic stainless steel properties: they possess martensitic microstructure. They are magnetic in all conditions and possess the best thermal conductivity of the stainless types. Hardness, ductility, and ability to hold edge are characteristics of Martin steels. They can be cold worked without difficulty, especially with low carbon content, can be machined satisfactorily. They have a good toughness. They have good corrosion resistant to weather and to some chemicals. They are easily to hot work. Composition, carbon content is 0.15 to 1.2 percentage, silicon 1%, magnesium 1%, chromium 11.5 to 18% of chromium. That is a Martenstick stainless steel. Uses of Martenstick stainless steel: pumps and valve parts, rules and tapes, turbine buckets, surgical instruments, etc. These are all the uses of Martenstick stainless steel. Effect of alloying elements. It joins chromium. It joins with carbon to form a chromium carbide, thus adds to depth hardenability, with improves resistance to abrasion and wear. Add manganese, it contributes markedly to strength and hardness. It counteracts brittleness from sulfur. Lowers both ductility and weldability if it is present in high percentage with high carbon content in steel. Nickel, it increases the toughness and resistance to impact, lyses distortion in quenching, lowers lessness distortion in quenching, lowers in the critical temperatures of steel, and widens the range of successful heat treatment, strengthens steels, renders high chromium ion alloys austenitic, does not unite with carbon. Vanadium, it promotes fine grains in steel, increase hardenability, impart strength and toughness to heat treated steel, causes marked secondary hardening. So molybdenum, it promotes hardenability of steel, makes steel fine grained, makes steel unusually tough and various hardness levels, counteracts tendency towards temper brittleness, raises tensile and creep strength at high temperatures, enhances corrosion resistance in stainless steels, forms abrasion resistant particles. Tungsten, it increases the hardness, promotes fine grains, resists heat, promotes strength at elevated temperature. Thank you for your listening. So this lecture, we will discuss about different types of engineering materials and their properties, and ferrous and non-ferrous alloys, especially for ferrous alloys. And ferrous alloys, they will have a low carbon steel, high carbon steel, and medium carbon steel, and tool steel and stainless steel, and etc., and their properties and application and other applications and other things. So this may be very useful for industrial person also and student community also. Thank you very much for your patient listening. Support this video. Why I am putting this end of this slide, I will put the aeroplane and rocket and all those things. It can all the materials, so many materials day-to-day life we are using. So all the metallic components are used for all the day-to-day applications. So this lecture is very useful for you. Thank you for your listening. Thank you. Thank you.